Mars, the fourth planet from the Sun, has long captivated humanity's imagination. Its rusty red hue, visible even to the naked eye, has inspired myths, science fiction, and rigorous scientific inquiry. Unlike its planetary neighbors, Mars occupies a unique niche in our solar system, a world that is neither as scorching as Venus nor as frigid as the outer gas giants, yet distinct in its geology, atmosphere, and potential for harboring life. This exploration delves into why Mars stands apart from other planets and examines whether life, if it exists or ever existed there, is likely to be water-based. Drawing on decades of data from orbiters, rovers, and telescopes, we unravel the red planet's mysteries with precision and awe. Mars is a terrestrial planet like Mercury, Venus, and Earth, but its characteristics set it apart in striking ways. With a diameter of approximately 6,792 kilometers, Mars is roughly half the size of Earth, yet its surface area is comparable to Earth's land masses due to the absence of oceans. Its thin atmosphere, primarily carbon dioxide, 96%, with traces of nitrogen and argon, is less than 1% the pressure of Earth's atmosphere, rendering it inhospitable to humans without advanced life support systems. Yet it is Mars's geological and historical features that truly distinguish it. Unlike Mercury, a scorched, airless world pocked with craters, Mars boasts dynamic geology. It is home to Olympus Mons, the solar system's largest volcano, standing 22 kilometers high, nearly 3 times the height of Mount Everest. The Valles Marineris, a canyon system stretching over 4,000 kilometers, dwarfs Earth's Grand Canyon. These features point to a geologically active past, driven by volcanism and possibly tectonic processes, though Mars lacks active plate tectonics today. Venus, Earth's closest sibling in size, is a hellish contrast with surface temperatures hot enough to melt lead, 460 degrees Celsius, and crushing atmospheric pressure. Mars, by contrast, is cold, with an average temperature of -60 degrees Celsius, though its polar regions can plummet to -125 degrees Celsius. Unlike Venus, which is shrouded in thick clouds of sulfuric acid, Mars's thin atmosphere allows us to observe its surface directly, revealing a history of change etched in its rocks and ice caps. The gas giants, Jupiter, Saturn, Uranus, and Neptune, are fundamentally different, composed mostly of hydrogen and helium, with no solid surfaces. Mars, as a rocky planet, shares more in common with Earth, but lacks the magnetic field and thick atmosphere that protect Earth from solar radiation. Its weak magnetic field, a remnant of a once stronger dynamo, suggests that Mars lost much of its protective shield billions of years ago, allowing solar winds to strip away much of its atmosphere. Mars's orbit, more elliptical than Earth's, contributes to its distinct climate. At its closest approach to the Sun, perihelion, Mars is 206 million kilometers away, and at its farthest, aphelion, 249 million kilometers. This variability drives extreme seasonal changes, with dust storms that can engulf the entire planet. These storms, observed by telescopes and spacecraft like NASA's Mariner 9 in 1971, highlight Mars's active weather systems, unlike the static surfaces of Mercury or the Moon.
The question of water on Mars is central to understanding its differences and its potential for life. Unlike Earth, which is 71% covered by liquid oceans, Mars today appears bone dry on its surface. However, Overwhelming evidence suggests that Mars was once a wetter world. Ancient river valleys, lake beds, and mineral deposits point to a time roughly 3.5 to 4 billion years ago when liquid water flowed across its surface. Orbiters like NASA's Mars Reconnaissance Orbiter, MRO, and the European Space Agency's Mars Express have mapped features such as the Neneti Valleys and Kasai Valleys, which resemble Earth's river systems. These valleys, with their sinuous channels and branching patterns, suggest prolonged water flow. The Gale Crater, explored by NASA's Curiosity rover since 2012, contains layered sediments and clay minerals like smectite, which form in the presence of water. The rover's findings indicate that Gale Crater once hosted a lake for millions of years, potentially habitable for microbial life. Mars's polar ice caps, composed of water ice and frozen carbon dioxide, are another clue. The northern cap, Planum boreum, and the southern cap, Planum australe, contain enough frozen water to cover the planet in a layer 11 meters deep if melted. Seasonal changes cause the caps to grow and shrink, with carbon dioxide subliming into the atmosphere during warmer months. Radar data from Mars Express's MARSIS instrument confirmed liquid water beneath the southern ice cap in 2018. A subglacial lake 20 kilometers wide kept liquid by dissolved salts and geothermal heat. Recurring slope lineae, RSL, dark streaks on steep slopes were initially thought to be evidence of seasonal liquid water flows. Observations from MRO suggested hydrated salts like perchlorates, which lower water's freezing point, allowing briny flows. However, later studies proposed that these streaks might result from dry granular flows, casting doubt on their connection to liquid water. This uncertainty underscores the complexity of Mars' hydrological history. Mars's water story contrasts sharply with other planets. Mercury has trace water ice in permanently shadowed craters, but no history of liquid water. Venus may have had oceans billions of years ago, but its runaway greenhouse effect vaporized them. The outer planet's moons, like Europa and Enceladus, harbor subsurface oceans, but these are locked beneath thick ice layers, unlike Mars's accessible surface features. Mars's past water activity, combined with its current aridity, makes it a unique case study in planetary evolution. Mars's atmosphere is another defining trait. Composed mostly of carbon dioxide, with 2.7% nitrogen and 1.6% argon, it exerts a surface pressure of about 6.1 millibars, compared to Earth's 1013 millibars. This thin atmosphere cannot retain heat effectively, contributing to Mars's cold climate. It also fails to shield the surface from solar and cosmic radiation, a challenge for potential life. The atmosphere's composition and density result from billions of years of loss. Data from NASA's MAVEN, Mars Atmosphere and Volatile Evolution mission, launched in 2013, revealed that solar wind stripped away much of Mars's original atmosphere. When Mars's magnetic field weakened around 4 billion years ago, charged particles from the sun eroded gases, leaving behind a thin veneer. Isotopic ratios of argon, 38R over 36R, measured by Curiosity, indicate significant atmospheric loss over time, supporting this model. Compare this to Venus with its thick, toxic atmosphere, or Jupiter's massive hydrogen-helium envelope. Earth's nitrogen-oxygen atmosphere, sustained by biological and geological processes, is a stark contrast. Mars's atmosphere, while dynamic with dust storms and seasonal CO2 cycles, is a relic of a once thicker envelope, possibly capable of supporting liquid water in its youth. Mars's geological record reveals a planet shaped by dramatic change. Scientists divide its history into three epochs: the Noachian, 4.6 to 3.5 billion years ago, the Hesperian, 3.5 to 3 billion years ago, and the Amazonian, 3 billion years ago to present. The Noachian era was marked by heavy bombardment and widespread water activity, forming river valleys and possibly oceans. The Hesperian saw volcanic activity and catastrophic floods, while the Amazonian is defined by aridity and dust storms. Olympus Mons and other Tharsis volcanoes formed during the Hesperian indicate intense volcanic activity. Lava flows and ash deposits reshaped the surface, while outbursts of water from subsurface aquifers carved outflow channels like Ares Vallis. These features distinguish Mars from Earth, where plate tectonics recycle crust, or Venus, where volcanic resurfacing erased older features. The absence of plate tectonics on Mars preserved ancient terrains, offering a window into the solar system's early history. Craters like Hellas Planitia, 2,300 kilometers wide and 9 kilometers deep, record impacts from the Noachian era. Earth's active geology erases such scars, while Mercury's surface is a static cratered landscape. Mars's blend of ancient and younger features makes it a geological time capsule.
The search for life on Mars hinges on water, the universal solvent for life as we know it. On Earth, all known life forms, microbes, plants, animals, rely on liquid water for metabolic processes. Water's unique properties, such as its ability to dissolve a wide range of molecules and its stability as a liquid over a broad temperature range, make it essential for biochemistry. But does this hold true for Mars? Mars's past offers tantalizing clues. The Noachian era, with its rivers, lakes, and possibly oceans, provided conditions suitable for microbial life. Curiosity's discovery of organic molecules like chlorobenzene and thiophenes in Gale Crater's rocks suggests the building blocks of life were present. These molecules, while not proof of life, indicate chemical complexity consistent with biological processes. Perseverance, NASA's rover launched in 2020, is collecting samples in Jezero Crater, a former lake bed with a river delta. The presence of carbonates and clays, minerals associated with water and potential biosignatures, makes Jezero a prime target. The Mars Sample Return mission, planned for the 2030s, aims to bring these samples to Earth for detailed analysis, potentially revealing microfossils or chemical traces of life. Methane detections in Mars's atmosphere, first reported by ESA's Mars Express in 2004 and confirmed by Curiosity, add intrigue. On Earth, methane is often produced by microbes, though geological processes like serpentinization can also generate it. The sporadic nature of Mars's methane plumes, detected at levels up to 7 parts per billion, remains unexplained, fueling speculation about biological or geological origins. Despite this evidence, Mars poses significant challenges for life. Its surface is now dry, cold, and radiated due to the thin atmosphere and weak magnetic field. Liquid water, if present, exists only in briny solutions or subsurface reservoirs. Perchlorates, detected by NASA's Phoenix lander in 2008, are toxic to most Earth life, but could allow liquid water at lower temperatures, potentially supporting extremophiles. Subsurface environments, like the subglacial lake beneath Planum Australe, are more promising. On Earth, microbes thrive in extreme settings, Antarctic ice, deep-sea vents, or acidic springs.
Mars's subsurface, shielded from radiation, could host similar organisms. However, without direct access to these regions, evidence remains speculative. Alternatives to water-based life. Could life on Mars use a solvent other than water? Hypothetical biochemistries propose solvents like methane or ammonia, which remain liquid at lower temperatures. Titan, Saturn's moon, has lakes of liquid methane, but its -180 degrees surface is far colder than Mars. Ammonia-water mixtures could exist in Mars's subsurface, but no known organisms use ammonia as a primary solvent. Water's abundance in the solar system and its chemical versatility make it the most likely medium for life, even on Mars. Mars's potential for water-based life contrasts with other worlds. Europa's subsurface ocean, kept liquid by tidal heating, is a strong candidate for life, but its ice shell limits exploration. Enceladus's water plumes, detected by Cassini, contain organic molecules, but its small size and distance from the Sun make it less dynamic than Mars. Venus's extreme conditions rule out surface life, though speculative microbes in its upper atmosphere remain a topic of debate. Mars's accessibility and evidence of past water make it the best target for studying water-based life in our solar system. Mars's distinctiveness lies in its transitional nature. It is neither a scorched inner planet nor a frozen outer one. Its geological scars tell a story of a wetter, warmer past, while its current aridity and thin atmosphere reflect a planet in decline. Unlike Earth, which sustains life through a delicate balance of geology and biology, Mars lost its protective atmosphere and surface water, yet retains enough similarities to Earth to fuel speculation about habitability. The red planet's proximity, 49 million kilometers at closest approach, makes it accessible for exploration. Over 50 missions, from the Soviet Mars 2 in 1971 to China's 2021 Tianwen-1, have studied Mars. Rovers like Spirit, Opportunity, Curiosity, and Perseverance have roamed its surface, while orbiters like MRO and ExoMars Trace Gas Orbiter continue to map its secrets. No other planet has been so thoroughly explored, yet Mars remains enigmatic. The search for life, water-based or otherwise, drives future missions. The Mars Sample Return mission could provide definitive evidence of past life. Proposed crewed missions, like those planned by NASA and SpaceX, aim to explore Mars in situ, potentially drilling into the subsurface for liquid water or microbes. Technologies like the MOXIE experiment on Perseverance, which produced oxygen from CO2, hint at future resource utilization for human exploration. ExoMars, a joint ESA-Roscosmos project, includes the Rosalind Franklin rover set to drill 2 meters into the subsurface by 2028. Its instruments will search for biosignatures in regions shielded from radiation. Meanwhile, astrobiologists are developing models to predict where liquid water and life might persist, from subsurface aquifers to transient brines. Mars stands apart as a planet that once mirrored Earth's potential but followed a different path. Its ancient rivers, towering volcanoes, and frozen water tell a story of loss, of atmosphere, water, and perhaps life. Whether life ever existed and whether it relied on water remains one of the greatest questions in science. Mars's uniqueness lies not just in its red sands or vast canyons, but in its ability to challenge our understanding of habitability and our place in the cosmos. As we peer into its past and probe its subsurface, Mars continues to beckon, a world both familiar and profoundly alien, waiting for its secrets to be uncovered.